We have already seen what will happen if we apply AC voltage to a resistor, and we have seen the phasor diagram for that. Now we are seeing what is the effect of when we apply AC voltage to an inductor. So here is the figure. So this is AC voltage and this is inductor. So here an AC source is connected to an inductor. Generally these inductors have some resistance, but here for simplicity we assume that inductor has negligible resistance. That means resistance in this component is 0. Resistance component is 0. Again we know V is equal to Vm sin omega t. That means voltage is sinusoidal. Again using Kirchhoff's rule, sigma epsilon t is equal to 0. Since there is no resistor, so this is the way we write this. V, that means voltage, is equal to minus L di upon dt. So how this term comes? If you remember, so what we have there? We had there epsilon is equal to minus L di by dt from previous chapter. So that term, suppose here voltage or potential is increasing, here potential will drop. So in this way we get this equation V is equal to minus L di upon dt. So this is positive term, this is negative term, and the sum must be equal to 0. So this is from Kirchhoff's rule, and this is the EMF produced or potential drop across this inductor. Here the second term is self-induced. So this is the self-induction that we have learned about in the last chapter. L is the self-inductance of the inductor and it works like an inertia. The negative sign is from Lenz's law. Otherwise potential will keep on increasing. Suppose if it is positive, potential will keep on increasing till infinite. So this must be negative. Now what we have here? So we have this equation V minus L di upon dt. This was our equation. From this, so let us put this equality here. V is equal to L di upon dt. Now di upon dt is equal to V by L. Di upon dt is equal to V by L, and value of V is Vm sin omega t upon L. So this is the equation that we get. So what is the meaning of this equation? So here if you take this quantity constant, because Vm is a constant, L is a constant, both are constant. So again this quantity is a constant. So this equation is saying that di upon dt, that means change in current is also sinusoidal. So there is a difference between current is sinusoidal or change in current. Current may not be sinusoidal, that we will see later, but change in current is sinusoidal. Slope di upon dt is sinusoidally varying quantity. Again change in current with time is sinusoidal with the same phase as source voltage. So this change in current has the same phase as voltage. Again this is not current, this is change in current. Now let us integrate both the sides with respect to dt. So di upon dt Vm upon L, again this is a constant, so it comes out of integration sin omega t dt. So we are integrating. So after integration what we get, this di will, this dt cancel out, this di will become I. So Vm upon L, this is a constant, and what is the integral of sin omega t dt? So integral of sin omega t dt is minus cos omega t, and again we will do the integration of this omega t and this will go into denominator. So minus cos omega t upon omega. So cos omega t upon omega with the minus sign. So here comes the minus, and we always add one constant in the integration. Two important things that we can see here: the change in current was in phase of voltage, the change in current, but current is cos function, current is not a sine function. change in current is sine function, but current itself is a cos function. So that means it starts from maximum value. It does not start from zero value. Now, how can we evaluate this constant? What is this constant? So let us see. So this is our wave. Even if we start from this 1 cos wave, so what we see that current is this side +1, this side -1. So current is equally going both the side. If this constant is there, if this constant is not 0, then current will not be symmetric. Current will go one side more, one side less, one side more, one side less, if this constant is not 0. But what we are seeing that current is going equally on the both side. So this constant must be 0. That means this graph is symmetrical around this 0 line. This is our 0 line. So it goes +1 here, it goes -1 here. Since both the values plus and minus are equal, this constant must be 0. So let us put this constant to be 0. Why? Because current is symmetrical. So here it is written. So EMF oscillates symmetrically. So so this constant is also 0. Now no constant or time independent component of current exists. So that means this component is 0. Another thing was that it is now a cos function. It is no longer a sine function. Change in current is a sine function. So we have minus cos omega t. So we can write this minus cos omega t as sine omega t minus pi by 2. So what we have, let us put this value here. Minus cos omega t can be written as sine omega t minus pi by 2. So I is equal to this term. Let us write this term be Im. So this is cos omega t is sine omega t minus pi by 2. So sine omega t minus pi by 2 minus goes into this. So what we get, I is equal to sine omega t minus pi by 2. So here what we have, Im is equal to V upon omega L. Im is equal to V upon omega L is the amplitude of current. So this is current. Again this is maximum current. The quantity omega L is analogous to resistance. So what was the case in resistance? In resistance we have this Im is equal to Vm upon R. Here we have omega L. So omega L is a thing which is equivalent to R. So this is equivalent, not resistance but equivalent to resistance, and this is called inductive reactance. This term is called inductive reactance. Omega L is inductive reactance, not resistance, inductive reactance, and we show it by XL. L because of inductance, and this reactance is shown by L, X. So X is general term for reactance. When we put L, this is inductive reactance. When we put C here, this is capacitive reactance. So inductive reactance is simply XL is equal to omega L. Now we get this XL is equal to omega L. The amplitude of current is then, what is current? Current, simply putting this value of omega L is equal to XL. Im is equal to Vm upon XL. The dimension of inductive reactance is as same as that of resistance, and SI unit is also ohm. So this inductive reactance X has same direct dimension as resistance, and its unit is also ohm. So this limits the current in the inductive circuit as resistance limit in a purely resistive circuit. So what we are seeing, this XL or inductive reactance is working very similar to resistance and limiting the current. The inductive reactance is directly proportional to L. Here we see this is directly proportional to L and frequency of the current. So it is proportional to frequency and this inductance of the coil. So what we can say, suppose if frequency is increased, inductance will increase. If frequency is decreased, inductance will decrease. Suppose this L is constant for a coil. If we change the frequency, if frequency is doubled, inductance, self-inductive reactance or inductive reactance will also double. If this frequency is halved, this inductive reactance will also be halved. This is one thing. Now, one important thing is that the source voltage and the current in an indicator shows that there is a current lag by the voltage by pi by 2. So current is pi by 2 behind the voltage. So let us see with this equation. So here, so what was voltage? V is equal to Vm sine omega t. Here we see I is equal to Im sine omega t minus pi by 2. So current is pi by 2 behind, because this is minus sign, that means current is pi by 2 behind the voltage in a purely inductive circuit.